Hello, my name is Julio Sanchez, and I'm going to present the paper Small Body Navigation and Gravity Estimation using Kalman filter and least square fitting. I would also like to thank you, my co-author, Professor Hans-Peter Schaub, for his support during this work. First, I'm going to introduce the topic, and main motivation of this work is that if a small body has not been visited before, the gravity field is not known and has to be sent with in-situ observation. The reason for that is that Earth-based sensor has a limited resolution on getting a shape or internal density of these bodies. There is also a need for autonomy during the gravity estimation process, and it's mainly due to constraint with communicating using with air using the space network. So accessibility windows to downlink observation data and uplink a gravity field solution from air is a very slow process overall. And you also like to quickly amend your navigation accuracy with a better gravity model, and also be sure that you can perform safe flight operations, being the homogeneous gravity field of this small body a major source of disturbance that could insert you in escape or collision trajectories. You want to have knowledge on how to avoid this. So the goal of this work is to develop a simultaneous navigation and gravity estimation scheme with the requirement of trying to being able to be accurate within the Virginia sphere. The reason for that is that a continuation of this project will be to perform landing and descent operations with the estimated gravity field solution. The proposed solution approach is to combine a dynamical model compensating center Kalman filter with the least square gravity field. In the illustration below, we can see how this works, and it is to fill a position acceleration dataset with the filter estimate. And when the data batches are full, you will make a fit of the gravity parameters and update your gravity solution. This process goes on and on after convergence is acquired. And now I'm going to detail how the simultaneous navigation and gravity estimations algorithms are. But first, I will introduce you the two dynamics that we are considering. We got the Kelperian gravity term, we got the inhomogeneous gravity term, and with the solar perturbations. We are going to assume in this work that the small body standard gravity parameter mu, the small body angular velocity and its center of mass, has been determined in a previous mission phase, so they are known perfectly. We also assume that we got knowledge of the solar perturbation parameter. So our noun is the inhomogeneous gravity parameter that characterize its acceleration term. We assume that we will have as a navigation device a camera that we will assume that is always pointing towards a small body center of mass in order to not account for attitude dynamics. Here is how this DNC UKF will work, and it's based on dynamical model compensation. So what we do is to extend the UKF state, position, and velocity with the model acceleration or unknown part of the dynamics in order to generate the position acceleration data set that we have been mentioning before. The UKF is mainly based on the sentence transform, and the sentence transform is a way to pass an initial Gaussian distribution through a nonlinear function and obtain its result as a Gaussian function. This is the core part of the UKF. Differently from an EKF who will linearize the dynamics, the UKF is fully nonlinear, but it's Gaussian. And it's also worth mentioning that it's a derivative-free approach being based on propagating some particles. How the process is set up, here are the dynamics of the process. The main idea of the dynamical model compensation is that in the derivative of the velocity, the model acceleration will compensate for the missing part on the inhomogeneous gravity. You see, that's the main idea. So we can generate the acceleration dataset. The accelerated model acceleration dynamics will assume a zero-ordered Gauss-Markov process, so they will be set to constant in between measurements. We will integrate this process with a Ford-Euler integration. Regarding measurements, we will assume that the measurements will come from a pinhole camera model that is able to track landmarks that add surface features such as craters that have been mapped in a previous mission phase. So instead of throwing directly like the pixels of the landmarks that are identified on the image plane to the filter, we are going to try to do an initial position determination and send that to as the measurement input to the filter. This can be solved geometrically in this type of problem if you are tracking to at least two landmarks. And the idea is as follows. If you make the connection between the image plane pixel of a landmark with its corresponding point on the surface feature of the small body, and you do that twice, for example, for two landmarks, you will see that they should intersect on the camera focal center. Assuming that the camera focal center is the spectral mass with a loss of generality because there is an offset that should be known in between, you can determine the spectral position. And this will not be true that the intersection is unique, especially because you will have like pixelization errors. You will not know exactly where the landmarks is, and etc. So if you got more than two landmarks, this intersection will not be unique. But you could say, okay, my position could be the minimum distance point in the least square sense to all the landmark spacecraft pseudo lines. Here I substitute lines by pseudo lines because, as I have told before, this will not be the actual landmark spectral lines. After some algebra, this problem boils to a simple linear 3x3 system where you can clear your spectral position, and that would be your filter measurement input. Accordingly, you can also obtain an estimation of your measurement of this position uncertainty covariance that could be used for the filter based on the residuals and a chi-square statistic of these residuals. Regarding the gravity models, one classical gravity model that is widely used in astrodynamics and in gravity field determination around small bodies is the spherical harmonics model. And the spherical harmonics model is characterized by its coefficients, and these coefficients that are represented in orange are linear with respect to the inhomogeneous gravity acceleration of this model. Then we are going to also consider trying to avoid this Virginia sphere divergence. Mascon model. A Mascon model is a model that tries to produce a gravity field representation, being the summation of point masses in a certain volume. That would be the small body. So you got like two parameters to play. You got the standard gravity parameter of each mass, and you got the position of each mass. In this work, we are gonna fit a priori the point masses. This is made randomly and try to be distribute them a little bit uniformly, assuming that the coarse small body shape could be computed initially. And so our decision variable for the Mascon model will uniquely be the standard gravity parameter of each mass. We are going to also impose a constraint that will make the center of mass consistent after a new solution of Mascons is obtained. So since both models that we are being considered linear parameters, you got this equation that relates the Jacobian, the decision variables, and the acceleration dataset. And you could try to fit this with a defining function that is the least square error of the summation of the acceleration residuals. So by doing that, and you got this objective function below, and that could be solved analytically by the suit inverse of the Jacobian, but that has some ill conditions in terms of numerical stability. So instead, what we are going to do is a momentum-based gradient descent algorithm to obtain the optimal gravity coefficient for both the Mascon and spherical harmonics model. So how is this being implemented? At the software level, we are going to use Basilis. Basilis is an IBS laboratory open source astrodynamic simulation tool that is based on Python modules that are written in C and C++. So you got all the easiness and flexibility of Python scripting with the background speed, execution velocity of C and C++. So I'm not going to detail this too much, but mainly at the left, we got the simulation process in yellow that will simulate the true dynamics of this environment. And at the right, we got the flight software processes, that is the simultaneous navigation and gravity estimation algorithms. Going to the results that we have obtained, we are going to first set up the simulations parameters. We are going to assume that the ground truth gravity model will be that of Eros with a polyhedron gravity model that has a constant density. We are going to assume a stable circular orbit located at a radius of 34 kilometers and 45 degrees of inclination. And we are going to place 100 randomly landmarks on the small body surface with a Gaussian error of 5 meters, 1 sigma for each one. So they are not perfectly known. That's the source of uncertainty in our problem. You can see the trajectory of the simulation on the right and where the landmarks, the random landmarks are placed. We're going to have a camera sampling range of 1 minute. We will have measurements each minute. And we'll have the lighting constraint. The lighting constraint will make that when the spectrum is on the shadow, it won't be able to track landmarks, and we'll have measurement gaps in our simulation. The simulation will last for 10 orbital periods, and each orbit, the data acquired for each orbit will then do a gravity fitting of this data and update the gravity solution. This usually theoretical gives for each orbit like 980 data points approximately. The filter results in terms of position are, as it can be seen, mainly we observe that there is a sharp increase in the error when the landmarks are lost and recaptured. Which makes sense because the solution of the position determination is more singular. And also the data set is made unavailable to the theoretical data set, assuming that measurements happens each minute and you can use them, is unavailable 22% of the time. We got measurement gap, and we are not going to use the data for training. It's very uncertain. But still in the central periods, we usually get position accuracy like below 5 to 10 meters, which is relatively good. Then we are going to show also the model acceleration estimation that the filter is tracking. And actually, that's a good result that the filter is able to track the model acceleration. And so the position acceleration dataset could be used to fit the gravity parameters. This is a fitting of a Mascon model with 400 masses, the final result. And what you observe, and you could get your attention, is that we have negative masses. We are not constraining them to be positive. We are not trying to do an internal reconstruction of the small body density, but rather a numerical approximation of the stereo gravity field. And nonetheless, we may revisit this aspect in the future. This is the global gravity solution for spherical harmonics model that we have analyzed and some Mascon models with respect to some orbital ranges of interest in the Earth system. We have added for comparison purposes also the initial knowledge, that is the point mass knowledge made by the black squares. So if we are below that line, we are making the initial solution better. And if we are above the line, we are making things worse. What we can see is spherical harmonics always fail within the unit sphere of the body, which is a non-issue that they diverge in that area. But nonetheless, using Mascon models, we avoid that. And still, the Mascon models are usually more accurate in all the analyzed orbital ranges. So the gravity error tends to be equalized at high altitude for spherical harmonics and Mascons. In the Mascon models, and we are using a random approach, we have done like 500 random distribution of them. So what we observe is that when we use more than 100 Mascons, the result does not vary too much with respect to each random distribution that we have used. In conclusion, the Mascon models are more accurate than the spherical harmonics ones that we have used. Here is an illustration. You will see a video showing how the global gravity solution is trained and how the error diminishes as you train each orbit. These initial figures, what it shows is the point mass error where you start with. So I'm gonna click. And below we have the spherical harmonics model or 4.4, which is one that is one of the best because it does not diverge so much within the unit sphere. And below we have one of the Mascon model. What you can easily see is that the Mascon model is reducing the error around the surface. You got less red area around the surface of errors, and this mitigates the spherical harmonics divergence within the unit sphere. At the end, like we got with this Mascon model, an 11% of average error remaining around the small body surface within the unit sphere, but still it's good, I guess, since we don't have data from that in the low altitude in the unit sphere that could make this estimation more accurate, but will involve taking more risks in placing orbiting the spacecraft at low altitudes. In terms of computational efficiency, we acknowledge that the Mascon model execution times may be typically 2 to 10 times slower than spherical harmonics, but still they are fast. The UKF step usually takes in the order of milliseconds for the Mascons, and the gravity fitting is in the order of seconds. And we have not used exploit the polarization that you can do with Mascon models. Finally, we can conclude with this work. So we have developed flexible strategy for simultaneous navigation and gravity estimation using landmass-based measurement. I mean flexible because we could consider other gravity model instead of just inserting the gravity parameters within the filter by using this dynamical model compensation approach. And we also have shown in particular that the online fitting of Mascon models shown to avoid the brilliant sphere divergence that happens with spherical harmonic without losing accuracy in other orbital ranges. Current work will focus on multi-spectral concepts where you could get less ambiguous measurements on different orbital regions, and also that will enable intersatellite ranging that could avoid the data gaps that happens when you are in the shadow of the small body, and also it's a very accurate measurement. In future work, we may also revisit some aspect of our Mascon model setup, or maybe consider the gravity representation such as neural networks, which is an active field of research in the ABS laboratory. Finally, I will conclude with the list of reference that is related or have inspired this work. Thank you for your attention.